So in a new project, you can give a name for the project and then the folder name. Same folder. Yesterday we were working, same folder you can. Okay. Then once you give OK, now you will be getting this particular screen. That is inside the additive window. Okay. There inside this, you can say your simulation configuration, let it be mechanical, types of simulation, manufacturing, and then in the manufacturing process stage, you can see three stages actually. Build is there, immediate release is there, and support room. Okay, three things you can see there. Okay. For example, I don't want immediate release. I want another option. Like you can see a plus sign just beside that one green plus sign is there. Okay. If you click on that plus sign, left click on that plus sign, you will get some additional stages like cutting, support removal, heat treatment, HIP, like that actually. Okay. Suppose I want to add one cutting stage. So on that cutting, you can just click. Then you can see one cutting stage will get added inside that, right? Okay. Suppose if I don't want to use immediate release, I will just click on immediate release and there will be an into mark there, red into mark. If you click on that into mark, that particular stage will be deleted. Okay. Now, let's say you have build, cutting, and then support removal. So that is the sequence in which you will be following for the operation actually. Okay. So build, second should be cutting, and third should be support removal. So everybody is getting that, the three operations. If it is shuffled up, just let me know. I will tell you how to move it. For example, if cutting is coming third, just let me know. I'll just tell you how to move that up. It's coming. So you can click on cutting. Okay. There'll be up arrow actually. Just below that red into mark, there'll be up arrow. You click on that up arrow, it will come second. Okay. So this is the sequence. Like we'll be removing the support removal and then as of now, we will do the three operations actually. Okay. Now you can give, after everything is done, you can just give OK to this window. Yeah, it is necessary. First should be build, then cutting, then support. Yeah. Then give OK. What about immediate release? Immediate release, both are same. Immediate release means it will release all atoms from the base. Cutting means you can give a direction of cutting, and we had seen the animation where it will incrementally remove the material. Like that we can do. Yeah. Right now we will keep the cutting. Okay. So now we can see on your screen, we can see there is a rectangular ball. This thing is a geometry, right? One cuboid is there actually with some fillet. So that is nothing but our base plate. Okay. So base plate can vary based on different machines. Like if it is a small machine, it might be 200 by 200. Like maximum base plate size up to now in the industry is 400 by 400. Okay. So which it depends on the machine, how your base plate will be. So which machine you are using depends on the machine that you see on the top. Like you can see on the top, there is a machine, parts, supports, like that you can see it. There is a window, right? On the top. Okay. Let me explain you what are those icons that are there on the top side. That is, there will be a yellow icon, there will be a green icon. Big icons are there actually here. If you click. Okay. So first one, when you click, you can see process actually there inside that. Okay, that is nothing but the process that we are trying to set. Whatever initial parameters we try to set, that will be the process. Next will be machine. Machine is nothing but what kind of machine you are trying to do. Then what parts you are importing, supports, material, base plate, everything comes in the machine parameters. Then there will be a green icon, which is nothing but the manufacturing window where we'll be defining our build parameters, cutting parameters, support room. Okay. Then there'll be a next one, which is nothing but our meshing window, where we can do the voxel mesh for the model or surface mesh or volume mesh, based on the requirement. So we'll be concentrating on the voxel mesh option here. So we'll be doing the meshing in that particular window actually. Next, one more window is there which is not highlighted. That is nothing but the result window. It will come up when we are trying to run the model. Okay, it will highlight. Up to now, there is no result. That's why it is switched off. Okay, so we'll come back to the first one. There is a process window, right? Okay, so process you have, or if you double click, you will get back that window which you had done earlier, like our process. Okay, that is our process window. You can close that. Come to the next yellow window. That is a machine actually. Okay, click on the next one. Okay. Now in that there will be a several like machine parts, things like that. So you can just give a click on the machine, double click on the machine. Okay. Once you double click on the machine, you will be able to get the machine properties. Okay. So what are these machine properties? So machine properties are nothing but according to the type of machine we are using, that is a 3D printer machine we are using, it will select our base plate dimension and our laser parameters actually. Okay. For example, there is a name and then there's a machine like that actually. Okay. At the side, you can see one drop down window actually, one down arrow. If you click on the down arrow, you will be able to see different machines like 3D systems, additive industries, concept laser, EOS, realizer, Renishaw, then Trump, and things like that actually. Yeah, these are all machine manufacturers which are there in the market actually. For example, if I'm going for a EOS, okay, if I drop down EOS, in EOS itself, different machines are there. M100, M280, M290, then M400 like that actually. Different models are there. So M100, it might be a small machine, like for building small parts. 400 might be a slightly, it will be a big machine with 400 by 400 build space dimension. Okay. So if I select 400, let's say, which one? Yeah, you can select anything, right? 400 or 290. If you select anything, you will get this particular parameters of this particular mesh. For example, if I select M400, you can see the build space dimension, which is there below, no? It will be like 400, 400, like that. It will be there. X, Y, Z dimensions. Okay. Is the plate size? Yeah, that is a base plate size. You can see. Base plate dimension. Okay. So the base plate dimension will be something like this. Based on the component will be required, dimension of the component. Yeah, dimension of the component. Yeah, and the volume of the component. For example, you have to print like 8 components. So you need a bigger machine. So the machine will be chosen according to the size of the components. And now you can give OK to this. Okay. Just give OK. So you can see based on the machine that you chose, the base plate thing also change. Dimension also change. Right. Now what we will do is we'll try to import a model from our Simufact tutorials. So what we can do is there'll be a on the top there is a icon there on the top corner. There'll be a icon with 3 red lines actually. Okay, can you see on the top menu? That is a menu icon. You can click on the menu icon. Okay. When you click on the menu icon, you will get like edit, you start, new project, and all those things, right? You take the demo option actually. Demos. Click on the demo. The last one. So then one more demo PDF kind of thing will open actually. Okay. So in that you can select the metal powder bed fusion. Metal powder bed fusion. That option. Inside that you will find one mechanical build stage. Mechanical build stage. Okay, you can expand that window. Measure. Code execution process. Double click on it. One option. See. Okay. These are the models. Yeah, it's amazing. So you in the mechanical build list, there is a aircraft component. One component is there. Can you see? You can, if you click that, you will get that actually. Aircraft component. So beside the aircraft component, you'll be able to see one folder icon is there. Then that is nothing but open project. Okay. Then there'll be open tutorial will be there. Okay. At the end, you can see some folder kind of icon. Yeah. Aircraft component. The third problem. So it will directly open the folder. Okay. Yeah. Just a second. Calibrated. So in the can you get that code? Yeah. In this, just click on this chat, it will go to this folder. You click on this aircraft component. Just click on the folder. Then you click on this aircraft. Then you can be getting some cat data. Try to report that cat. It's still you're able to get the cat data. So we have to open it. Yeah, I just get. So everybody get it. Not it. Can you go to the aircraft folder? You know all of muscles stored. Folder. Come to aircraft. Then CAD data. Yes. Okay, then step file. So there'll be a step file inside. We'll try to import that step file. Okay. So you can copy this path actually up to this CAD data. Like copy. Okay. What you do is you can go to this parts here in the simulfactor. After the machine, there will be a parts icon, which will be red in the this thing. Machines. Yeah. Under the machine. In the machines, in the machine window, when you click on that yellow icon, yeah, no need to click. You can click. You can copy this part. Parts. Trying to import that part. Parts is next step. You can come back to parts. In that parts, I will tell you. So in parts, you can. You copy this part. Copy this part. Parts and okay. Then parts. In parts, if you right click on the part, there will be import option. Will be this. On that just like keep your mouse on the parts and then say import. Okay. Then click on import. Okay. It will ask for import geometry. You can copy your whatever path we copied. You can paste it there and then say enter. Okay. So if you click on like all files, it will show you the step and this thing here actually. 13MF file. We'll click on the step file and then we'll open it. Okay, just click on the step file. We'll open it. It may ask for some import options like that. Just say import. This what we are trying to do is we are trying to import a CAD geometry from the simulfactor support directory, whatever is it. Okay. Next, if you try to import, there will be one more window will come. So now you can see one part is there already. Yeah, it's better. The first one, step 5. Yeah. Sorry. Now it has come over here. Okay. Import. Now it will come somewhere in the corner of the base plate. It may not be positioned in a right way, but it's fine. Okay. So now to position this, we can use like there'll be a option called position of geometries, which is unticked there. Like after there is like it will show first it will show the dimension, then geometry option, then it will show you something called unit, then it will show position of geometries. You can click on the position of geometries. Okay. Which would they just change it to like weight. Now just say there is something called distance to left, distance to front, distance to bottom, something like that. Okay. So can you click on the button which is next to distance to left? You will be able to see that positioning to the middle edge, right? And if you say distance to front, it will say it will come in the center of that plate. Okay. Now distance to bottom. Distance to bottom means how it is there from the bottom of your base plate. Okay. Let's give a distance of, let's say, 5 mm. Can you give 5 mm? Just modify it 5 mm. So you'll be able to see now the component is placed in the center of the plate with a distance of 5 mm gap is there, the base. Okay. Then give OK actually here. Now you have imported the component. Now it was and you say at least say 5. So it is equal to yes, so it's height of 5. No, if you model in that we keep that mm. Then there is no risk. So now what you do is you got the component inside the base plate. Okay. Now what we do is we'll go to the next option. That is after parts, there is supports option. Okay. So if you click on the support option, so you will get something called part group like that actually. Yes. Okay. You can double click on it. Can you double click on it? So it'll open a new window where you can generate your support structures. Okay. So for example, I'll just click on the button generate supports. There will be a button just below the CAD's additive. There will be a generate support structure option. Okay. So it will start generating some support structures actually. Okay. Can you see the support structure getting generated? Yeah. Okay. So these support structures are generated based on certain parameters what we have given here. Like there are a lot of parameters are there, like critical angle, okay, then method, okay, method, CAD's additive, simufact, like that 2 methods are there. And type of support. There are different types like blocks, overhang blocks, block line, and things like that. So if you want to know details of the support, it is given in the support. There will be a documentation just below information will be there. One blue, icon will be there. You can click on that. You will get the related information regarding the support structure. Okay. So now, just now we'll give okay. Let it be default. No, just give. Yeah, default. Just give it. So now we have the part, and you have the relevant support structures created on the component actually. So since we left a gap of 5 mm from the base plate, it has generated the support structure below your component. Okay. And all the other regions also you can see wherever necessary, it has created the required support structures. Now we'll go to the material. So can you click on the material? Double click on the material. So in the material library, we'll be able to see all the most commonly used powder materials for the metal additive manufacturing. Like it can be a ALSI powder or Inconel 625, 718, MS1 powder or titanium powder, all these things actually. Okay. So let's say we just select ALSI 10 mg, that particular option, and say give OK. Okay. So this will apply the particular material to the component actually, whatever we are trying to print. Okay. It is there in the material. You can select the ALSI. Yeah, you have to open up the particle size to be able to customize over here. It is I think very because each manufacturer of some cases size may not be very common. Suppose on laser, if you are using to go for the stage, you are something very or if we are using high power laser, we want to make thick blocks, maybe 1 mm will be ready to be able to fix it. Or else they may have the standard sizes. If you're taking the pillar metal, you will go to find its own prices. You need to do the they have tested and ready. Since because the external work is supposed to justify the size, and go for 10 or 7 and we are checking what is the average size and then we are filling the material samples. So we have the properties of like there is the measurements we use for we temperature. It's very I don't know, but it's tested and yeah, so now we generated the support structure for this. Now what we can do is we can click on the base plates. Can you click on the base plate? So base plate, there will be two options. Either you can consider the base plate as a rigid, or if you want to know the deflection coming in the base plate as well, we can keep it as a deformable base. That is, we can assign material to the base plate also. Okay. So when you click on the base plate, there will be something called consider base plate deformation. One option will be there. Okay. You can click on that small window. It will prompt for the material. Okay. So you can add import, you can say under, if you click on that consider base plate deformation, it will say material actually. That time there will be a small icon on the side. You can click on that. It will take you back to the base plate material. So base plate material, you can choose the material, the base plate material based on the real machine parameters. So let's say we can choose, let's say 316L base plate. Okay. You can say okay. So now the base plate property has been added. Okay. So now we'll go to the next, that is manufacturing win. You can say the icon, that is a green icon actually. For support, yes, we can select the material. No, support will be the same material. Same as the part. Because it is the same powder, it is getting printed. Okay. So the next one will be the green icon. That will be the manufacturing, you can say manufacturing icon actually. Okay. Yeah. Optimization, there will be stages will be there. Okay. Stage, build stage, cutting stage, support removal stage, like that. Different options you can see. You can double click on the build stage. Double click on the build stage. Okay. So in the build stage, you will be able to see some parameters like layer parameters, like hash type, then something called inherent strains actually. Okay. So this inherent strains is what we were discussing earlier, where we are doing some calibration and finding these values actually. Okay. That is called inherent strains. So these values actually comes from the calibration. But as for this tutorial sake, we will use the material, calibrated strains, which is already available in the database. So let's say on the top, you will find one build parameters, name build parameters like that. You can take the drop down menu there actually. Okay. So you'll find already two materials will be there, one aluminum and one titanium, Ti. You can choose that aluminum one. Okay. If you choose that aluminum one, you will see that already the strains that are calculated for that particular material will be already available actually. Okay. Then you can say okay for this. You give okay. So your build will be done now. Now you'll go to the cutting stage. So cutting, yeah. But still we are going to do this. Also, okay, cutting, cutting should be. So because once you get actually paint the color, yes, yes, yes. And also the sequence is changing. Cutting. You can change it at any stage. Any stage. Before running any stage again. So now, if you go to the cutting, you can see there is one cutting window will come. Under that, in the GUI, you can see one square, you can see one plane is coming actually there. Okay. That plane defines the height of your cutting and the direction of your cutting. Okay. So if you say there is a, if you see in the cutting properties, there is something called the height actually. Okay. So that height is nothing but the height from above the base plate, from where you will be cutting the component. It can be in reality, it will be a EDM wire cutting, such kind of process actually. Okay. And the height you can just mention there, since you gave a gap of 5 mm. Yeah. You will, let's say you will use a height of 2 mm to cut the component. So you can mention that height there actually, 2 mm. This height is from the base. Yeah, from the base plate. So if you change the height, you can find that the plane height also will change. Okay. So one thing we need to take care is that we should not. Metal will be there. The removal of there will be. Okay. So if you can enter 2 mm and just give OK actually. Okay. So sometimes what will happen is when we are leaving a gap of 5 mm, if we give distance more than 5 mm, it means that you will be cutting the part also actually. That should not happen. Okay, so the cutting should be within the gap, within the gap which is between the part and the base plate actually. Okay, that should be taken care. Then comes support removal, the next step. Okay. In support removal, a lot of things you can do. Like there are several supports that are generated at different regions. You can remove all the support at once in the simulation, or if you want a sequential removal, like let's say this part you want to remove first, and then this part, then this part. You can define your sequence also in the support removal. Those options are available. But as of now, let's say we'll remove all the support at once. So you can see one assign all support. One for left side, one double arrow is there. Towards pointing towards the left, you can click on that. So it will add all your support structure to the assign support structure window. Okay. We can, that I'll tell you, sir. In the next one, I'll tell you how to run. So then you, okay. Okay. So now you can see if you give okay for that, all the, stages, it will become white in color. Nothing will be written in red color, right? Once you give okay. And also you can observe one more thing, like on the top, that icons are there, it will be green color, like this. One green line will be there. Okay. If you have not defined anything inside that window, you can see that there will be a red line will be there, which is showing that it is incomplete, like that. Okay. Something need to be defined or something we have missed out. It denotes that kind of thing. Okay. Next, can you go to the next icon? That is a blue. Okay. That is an analysis window. In the analysis window, main thing we have to do is the that is something called the voxel mesh. There will be something written in red color, voxel mesh. Okay. So that voxel mesh we need to select. You can double click on the voxel mesh. So this voxel mesh is nothing but the mesh where our calculation will happen. And then at the end of it, it will be mapped onto your whatever, the surface that you're having on the component. It will be mapped. So what we will do is we will try to create a voxel mesh on the surface edge. Okay. So if we can use all the default values as of now, just say generate mesh so that we can see how the voxel mesh looks like. Okay. So you'll be able to see, cuboids, small cuboids, which is covering all the base plate, your support structures, and then the component. Okay. So this is called as the voxel mesh. Now, I'll just say okay now, just hit okay. Okay. So now, if you hit OK, you can see all the things have become green in color, that all the lines are green under the icon section. Okay. This shows that we are like in a position to proceed to the run action. Okay. So to run the thing, there is a green icon, start analysis icon will be there, green arrow on the top. Okay, you can click on that green arrow. It will prompt you to save the project. You can just say okay. Yeah. Next to say start analysis. Okay. You can say some this thing might come. I think this is related to parallelization or something. You can just say allow for all of this. So now it has started the analysis. You can see once it result starts coming, it will come to your screen actually. So this will, start building the component layer by layer. Okay. No, yeah, use this one, man. You can use the login. Login but change many number of as per those parameters, how it default. That's the Zoom login பண்ணாதான் பண்ணிருங்க அதனால ஒரு ஸ்டார்ட் தொடர்ந்து பண்ணாதீங்க சிஸ்டத்தை லஞ்ச் பேட் வந்து நம்ம எல்லாம் கண்டிப்பாக வெல்டிங் ப்ராசஸ் கேட்பாங்க உங்களுக்கு ரொம்ப யூஸ்ஃபுல்லாக இருக்கும் கரெக்டாக லிட்ரேச்சர்ல இருந்து நீங்கள் இமேஜோ பேராமீட்டரோ எடுத்து நீங்கள் ஃபீட் பண்ணி அதையும் நீங்கள் கம்பேர் பண்ணி அந்த டெம்பரேச்சர் ப்ரொஃபைல் ப்ளீட் ப்ரொஃபைல் அதை வச்சு நீங்கள் இன்டர்பிரேட் பண்ணணும் அந்த லிட்ரேச்சர்ல இருந்து டேட்டா நீங்கள் எடுக்கிறதுனால அவங்க எதுவும் கேட்க மாட்டாங்க இமேஜ் யூஸ் பண்ணாதான் கேட்பாங்க பர்மிஷன் வாங்கி டேரெக்டாக வாங்கி 54 ட்ரையெல்லாம் பண்ணி மீட்டிங் பண்ணி போட்டுப்பாங்க எல்லாத்தையும் கம்பேர் செய்ய மேல டெஸ்க்டாப்ல சின்னதா ஒரு டெக்ஸ்ட் டாக்குமெண்ட் இருக்கும் டெக்ஸ்ட் ஃபைல் எம்எஸ் வேர்ட் இல்ல நார்மல் நோட் பேட் அந்த மாதிரி தெரியுமா அதுல பார்த்தோன்னா மீட்டிங் ஐடி பாஸ்வேர்டு வச்சிருக்கேன் இல்ல மீட்டிங் ஐடி பாஸ்வேர்டு வச்சிருக்கேன் இதுல இருக்க டெஸ்க்டாப்ல ஒரு நோட் பேட் ஃபைல் ஓகே You can use this advanced to remake this. If it is a backward, you can remake this and generate this. Like NIT extra clearing model. Or if you have done some machine like Apex or something, like yesterday we did for that. There we have certain expressions we can improve them. Then we can improve that one. After that, we go for even R12 process, we can say possible. And the forming is also there. But number of forming will be very, yes, we can continue that question building. Now you can see the model running and say take some certain amount of time. After that, maybe something. We completed this one. This one is completed. This one is completed. Now it will run and we will see the results once it goes. Then okay, sir, we'll go for lunch. Yeah. Dear participants, we are go for lunch. You can join by 2 o'clock. Okay. Thanks. All are please join our session by 2 o'clock. We have submitted the models. It will run for a while. So once results are came, we will share the results with you and we can start the new session. Thanks for coming. Join the session by 2 o'clock. Thank you. So this is showing the displacement plot, like total displacement plot that is showing after it is built and after it is cut from the base plate. Okay. So various result you can see on this part of the screen, like on the top, there is some displacement is there, equivalent stresses. Okay. So you can, if you put the equivalent stresses, you will be able to see the residual stresses that is coming from the on the part after the printing is done. Okay. Then you will be able to see Z layer displacement. This Z layer displacement will give you the displacement which is in the vertical direction. That is in your axis. If you see, the Z is the vertical axis. Okay. So taking that as a reference, you will come to know how much is your displacement in the Z axis. So if you get like more displacement in the Z axis, there are chances that the part will get collided with the reporter. So for that, there are different results are there. Like there is next result called manufacturing issue. In the manufacturing issues, there is a result called reporter contact. Okay. So reporter contact, it will show you any region, any chance of getting contact with the reporter line. If it is a full green in color means it is showing that there is no reporter contact. Okay, it is safely it can be printed like that. Then comes possible failure. So any kind of failure can be possible. So if you play that, click on possible failure, and if you play that animation from the start, okay. So you'll be able to see in some regions there might be some red patches here, actually. Here. Okay, so these patches will suggest that maybe some kind of failure, that is, stress-based failure can happen in those regions, actually, support structure. Okay. So you can see those kind of things. So red means high risk of failure. Okay. And yellow means there is a lower risk of failure, but maybe some chances will be there. Risk chances are more. If it is green, there is no issues actually. Okay. Yeah. Yellow is nothing but increased risk of failure, but it may pass. But red is like high risk of failure actually. It might, go for some failure actually. Then you can find further results. The temperature results you won't be able to see here because we ran a mechanical analysis. For we can see the thermal output as well. Okay. Then if you see some more like how to post process, you can see if you right click on the screen, you will be able to see some view tools actually, like clipping. If you right click on that, there will be some view tools will be there, like clipping, then measuring, and then query dialog. Like that, you will get 3-4 options. Okay, here down view tools. If you right click, you will be able to see below the show undefined there. Okay, one pad with the scale, and then one node, and then this thing one cut sliced geometry might be there. If you click on that sliced geometry icon, you will go to the clipping plane properties. Okay, that sliced one, the first one. Okay. Then if you see one plus sign will be there, one green plus sign. Okay. If you click on that, there'll be 3 axes, X, Y, and Z, and some view axis. If you click on X axis, let's say, you can see that the clipping of the model will be done with respect to your X axis as your normal edge. Okay. If X is this direction, the clipping plane will be normal to your axis. Okay. That is called the X axis clipping. So using this clipping plane, you can move this clipping plane like this, and you can see the results in the intermediate layer section, whatever is going on actually. Okay, for example, like this, you can see, for example, if I put it to, let's say, equivalent stress, I can see at those cut sections, what is the stress result or whatever result you are plotting. Okay. Yeah, because that maximum values might not be changing because of that. You can see here actually, if you can right click here, display min max nodes. So display for parts. It's like this. So leave that place. So we identify the Maximum.
Yeah, identify the properties like.
Yeah. Yeah, that we can do. For example, we say half model cut plane. Okay. If you see, you can take only the cut plane at a particular section like this. Okay, that option is available here actually down. If you say there is something like a box, no, some third one actually, half model cut plane like that. If you see that, it will show you that properties only for that cut plane. Okay. Then you can go to one more option called this. If you right click again, right click on the screen again, there'll be something called open query. Okay. Just after that in the view tools, the third option, query tool. Can you open that query tool? Okay. And just try to select anywhere on the model edge on that. Yeah. So there you'll come to know at that particular location what is the value properties.
Where?
Okay.
This one.
Yeah. Okay. So there you'll get exact values. Like here it will be showing you an entire value, range of value. But to know what is the exact value at a particular location, we can use a query tool. Okay. You can place your query tool or that thing in multiple locations actually.
One by one.
Yeah. One by one. So you'll be able to see the values on the, for example, there'll be a window coming. In that window, it will show you at point number 1. This is your value, this is your value. Okay. If you move your slider, I think you'll be able to see, like if you move further, you can see at each and every location. Okay. If you click on a particular location, you'll be able to see the value at that particular plane actually. Okay.
What's the displacement?
Yeah, this will show whatever is plotted on the range plot. It will show the same value. Okay. Now let's say you need a time history plot of a particular. Yeah.
So that is you go to the correct. When you click on it. Again, I can use take that out. And that is what says I had. If you do, if you look to the temperature also.
These tools are common for all the software, like welding, for everything. You will find similar tool for this post processing. Then there is one more. Hey, can you come to this result button? This last that square result square button is no. Can you click there? So you will be able to see surface results. Okay. So when you right click on the surface result, you will get an option called shape comparison. Shape comparison. Okay. You click on that shape comparison. Okay. Then what you do is there will be one colorful box will be there. Okay. You can click on that box. Yeah. Then one blue arrow will be there. Called apply button. Yeah. You click on that blue arrow. You will see that the body will like fit with the result actually. Okay. So why do we do this? We are trying to see the deviation of your CAD model with the printed part. Okay, so what will happen is after manufacturing, there will be a surface deviation due to different effects. The geometry will not be as per your initial design. There will be a deviation. Okay, so we want to know how much is the deviation. Okay, so from the initial, there will be one more. Can you click on this down one colorful icon? Just click on that. Okay, so here you can see the maximum deviation has been 0.73 or whatever you are getting on the screen in the red color. Okay, So if you click to, just zoom to that red location, you can see the deviation, like there will be one transparent part, one transparent thing will be there, and one solid. Like you can see a transparent part here actually.
Yes, sir. Yes, sir.
Okay, if you zoom it, you can find here. If you see the screen here. So this is nothing but the how much the geometry has deviated from your initial. This green one, whatever is shown, that transparent part is the original. Initial part, CAD model that you took, imported, and you did the analysis, right? That initial CAD model is this.
But
Okay.
our analyzed part is inside that.
Analyzed part is this, the deviated, the colorful one. That is the analyzed.
So that means the shrinkage is.
Yes,
Like
that means some shrinkage or some, displacement happened like this.
Yeah.
Here you can
But
see.
it is inside only.
Yeah, it is the inside. It is shrinkage or
Yes, shrinkage.
shrinkage has happened actually. Okay. So you can see from this, you can understand like how much it has deviated from your initial geometry. So most of the time, these issues can happen during the additive manufacturing process. So what they do is they do something called pre-compensation or optimization. Okay. So inside the Simufact, if you go to the optimizer, there will be in the third green, you can say box. At the before the stages, you can see one optimization window. Okay. In that, the first one, there will be a distortion compensation. Okay. If you click on that, distortion compensation, it's not coming.
Checkbox.
It's not clicking. Huh?
Yeah.
Okay, maybe check that out. Okay, maybe this result is there. What I'll do is you can do one thing. Yeah, you can do one thing because why it is not clicking is already these results are available in this process. Okay, so what you need to do is you can just make a copy of this process. You can right click on process and just say copy. Okay. Copy and then say copy without results. This copy. Yeah, if you right click on this processor, you can just right click. On this thing. If you go to the first icon here, the process will be there. Okay, with green color. So if you right click on that green color process, you will find one copy option, third option. Then you do copy without the result. Okay, so it will make a same copy of the existing. Yeah, just processor. Right click on the process, copy without result. Yeah. The first one, the first icon, the first yellow icon. On the top, yeah. Copy without result. Okay. So you'll get a process hyphen copy like that. Actually. Okay. So then you go to the optimization. Then if you try to click on that distortion compensation, one window will come. I just tick on that. Just click on the tick. Yeah. So now there is a part here which is your original part, which is there here. Okay. So you'll click on that part. Here there will be a click. There'll be an option to click that part. Then it'll ask you what is your acceptable deviation distortion you want actually. Okay. So let's say you want like your part to be within the 2% tolerance. Okay. So you will just mention like 0.02 like that actually. Okay. 2% or 0.02 mm like that. You'll put a value over there. Actually. Okay. So once you put this value, what it will do is it will if you give OK and run this, it will first give an initial run. It will compare your initial CAD with the original CAD. If it is finding that anywhere the deviation is more than 0.02 mm, it will do one more iteration. Okay. Like that, it will do 3-4 iterations and bring the distortion down actually. It will compensate the geometry such a way that you will get your right part printed within the acceptable tolerance. Okay, so that is called the distortion components. Okay, so you can try just give OK and just try running this model. Actually, it may take some time, but we can try that out. Can run it for some time and then maybe after the training also we can directly start that. So once it starts the analysis, yeah. Okay. Once it starts the analysis, now the result will start appearing. Okay. So once the result starts appearing, you can click on the last box, the result box. Yeah. Last result box, you will be able to find one extra option, distortion compensation result, like that. You can click on that. So this will show you a graph, like what is your maximum distortion versus the step actually. Okay. So right now we are in the first step. So after the first step completes, it will show you a graph like this, like what is your maximum distortion. Until it reaches the 0.02 value, it will keep on doing the optimization.
After that, you can see. So this will show you at the end of it will show you. The distortion will be reduced to below the point.
So like this, once we get this part, we can export this part as a output file, like an STL file, and we feed it to the 3D printing machine.
Once they get this, so how can we save this results as millions like that, sir, per day?
Yeah, we can. For that, I think we can.
How can we save this results, sir, in like JPG or
JPG,
PDF?
yeah. So for that, I think.
Yes, we have to take results also.
Yeah. That was a. Yeah, here it will be there. Here, if you see, there will be icon. So down, there's a camera kind of thing, no?
Yeah.
So then in that camera, you can see save image. Okay, save. Yeah, it will save. You can save it now also, I think. If you save image like this, you can get save in all these forms. Okay. See, you can save it in your PNG format, JPG format, all these formats, you can save that. And if you want animation, you can save animation like that. Yeah, you can close it. Okay. So this is started doing. Once it completes, it will start the next subsequent cycle actually for compensation. Okay. If you want to save the animation, animation there is the option. The camera is the
Once the process is completed, animation.
yes. You can save it. Okay. So this is the like a workflow for the additive manufacturing. For the you can say the mechanical method actually. So for this mechanical method, actually we need to do something called a calibration. So that maybe I'll show you you can say a PDF file. You can go through that PDF file. How do they do the calibration? Whatever I showed in the morning. So they create one cantilever beam. They print in the same way. Like instead of the real pattern, they will print the cantilever beam actually. Okay. So that cantilever beam will do some calibration techniques and find inherent strains. That inherent strains will be applied to the model. That's how we do the ENGG manufacturing problems. In spite of this one, like I'll just kill this run now. Stop analysis. If you want to stop the analysis in between, there is a if you click on one process, on the top you will be able to see one circle with a square, white square in the middle. This will stop the analysis. It's to kill the runtime. Okay. So once the analysis stopped, it will be in an orange color like this, saying that only a portion of the result is available. Full result is not available. Like that. So now what you can do is you can also try copying resume. There is a, I think you have to use directly you cannot resume. I think we need to do that in the behind solver actually. When solver will be running, there we need to go and invoke that again. Right now I'll delete this result. Let's say delete. You can change this to a thermomechanic. This process. Yeah. So you can process copy is there. You double click the process copy. You kill that, sir. You stop that one. Like you can right click. Click on it. That right button. Okay. So once it stops, it becomes like an orange color. That bar, that status bar will be orange in color. So some results are there in that. Okay. You can also go this thing and clear those. If last channel remove it will become an empty process again without results. Then you double click on this process. Process copy, sorry, process copy. Then you change it to thermomechanic. Okay. Then give OK. And then you can go to the build option. So in the build, if you take the build now, that third icon, if you double click on the build, you will be able to find some extra things like it is asking power, speed, efficiency, then spot size, and all these parameters actually. So why it is asking these parameters? Because we are changing it to thermomechanical. Okay. In thermomechanical run, what it will ask, since we need the temperature outputs, we need to apply the laser parameters also to get the thermal output. So laser parameter in the sense, what is the power of the laser? Then what is the beam, the speed of the laser, and what speed, velocity it is moving. It is like a welding analysis itself. Right? You can say a welding analysis itself with, but it is additive method. So you'll be able to see some parameters already defined there by default. Thermomechanical, then you go to the you okay. Then you go to the third item, green. So double click on the build. There you build. So if you click OK here, let's use the default parameter. And you do a voxel mesh again, actually. There will be a this thing, that voxel mesh and you need to regenerate again. Okay. Just click on it and generate mesh. Click on generate mesh. Generate the mesh here because we are solving a thermo. Give OK. It will create the mesh again. Now you can try running this one. Can you start the analysis? So two things here, like we change our mechanical analysis to thermomechanical, and we gave some the laser parameters, how the laser parameters of the machine. Okay. So now what it will do is, like a welding analysis itself, it will do a thermomechanical analysis. it will give you for each layer what is your temperature result. At each layer, what is the displacement, distortion, whatever we saw yesterday in a welding. In a similar way, here also you will get the result. Okay. So you can see the first result is coming. Like first it will lay a particular layer. It will start heating that layer. Actually. Okay. So that laser will come and heat that particular layer. You will be able to see the temperature slowly increasing at the layers. Okay. Then it will cool down. Because after the laser power is off, the it will solidify and it will cool down. Then again the next layer will be laid. So like that it will build the component. So here you will be able to see the temperature results also, like P temperature. Okay, temperature. Then all your thermal results also will be available in the thermomechanical. Okay. So you'll be able to see the using that query tool. You can check the temperature at each different locations. Okay. You can put a probe at different location. You can check the temperature output, which is coming at that each and every location. Okay. It will show
this during the deposition or
this will be like first it will put the this thing powder, then first the deposition will happen, then the laser will come and heat, then it will cool down actually. Okay, so all the thermal history will be captured in each layer. Heating, deposition, heating, and cooling. So this is like how we do a thermomechanical. Okay. So I just kill this one. Okay, so whatever we are like discussing now, I'll show you the document, the tutorial files where these things are available. So maybe after this thing, if you want to practice this, you can use this tutorials. So in this, on the top, what do you call it? The file icon, no menu icon. If you click on that, you can just browse to this particular tutorial and training. Okay. Just put the arrow button. Click on the tutorial and training. This will open a PDF file actually. Okay. So you can see mechanical simulations. If you see, you can get a PDF. In this PDF, you can see the examples that we are working on. For example, this particular model, mechanical simulation model. Okay. So all this data is given here. Okay, this is one PDF. And other than this, there is also demo problems available. This demo problem we already took in the morning. Like we went to the demos and we clicked on this particular model. Which one? Demos. Huh? Yeah, you can click on that. Sir. That aircraft component only. In that aircraft component, if you the second button is there, open tutorial. Aircraft button, aircraft tutorial. The second one is there, second icon. Yeah, that one. Yes. If you open that, you will get a window like this. I mean, you will get a PDF file. Can you see that PDF file? Yeah. This is the same problem that we were working on, right? Everything like a step-by-step procedure, you can get it so that you can practice it later also.
Sir, this PDF is readily available. So, why? With you.
Yeah. This is there in your directory itself. Yeah. In your, I'll show you. It will be in SimuFact. There will be a SimuFact folder will be there inside your this thing. Okay, there you go to additive folder 2023. There will be something called doc and tutorial. So if you go to additive, SimuFact, D folder, SimuFact folder. Inside that, go to additive folder. Inside 2023.4 doc, there will be a folder called doc. Inside that, you go to tutorial and chapters. So this will give you, like, for example, if you open this particular quick start, okay. So this will open the PDF file for you. So everything in PDF is available inside.
Same building also.
Welding also will be there. So welding, if you go inside the welding.
Yeah, is there.
Oh. Okay. Now, what we will try to do here is, we got some idea on how to do the additive method. So, what we'll be doing is we'll be taking a problem. Next problem, we'll do a welding analysis. Okay. So, welding analysis means let's try to make a geometry. Let's say some two plates we can take like this, like a butt joint. We can create a, I can say, groove, and we'll create a filler inside the groove. We'll do a welding analysis. We'll try that actually. Okay. So for that, we have to open the Apex again. Yesterday, what we did,
We can close it.
we can close this additive. Okay. So let's practice one more welding tutorial so that we'll get an idea how to use the the welding GUI as well as the Apex software. You can open the Apex. Yeah. You can open a new file. So here, yesterday we saw like the beads we created inside SimuFact window. So today what we will try to do is we'll model the beads also, weld beads also here, that the filler. We'll export the filler along with the model. And we will use that filler as a bead source. Okay. So let's create that model actually. So first what we will do is we'll go to the sketching mode. Yeah.
2 points.
2 points we can create. Second. Just a minute.
First start. So tell me the dimensions.
Yeah,
Everyone follows.
Yeah. I'll tell the rest.
Yes,
So rectangle with 2 points.
Right, sir.
Yeah, not open. Okay, let it open. Once you open, you can let it. Okay. So we'll take yesterday's like rectangular with 2 points, rectangle with 2 points option. Yeah. Rectangle dimension, let's say 200 by let's say 10. Okay, 200 like say length and then 10, let's say the thickness actually. Okay. So just be in the sketcher view only. Don't go outside the sketcher view. Then there is a one more option. Here you see one chamfer option is there. Here. Like point, fillet, chamfer. Okay, click on the chamfer option. Yeah. So you can you click on the chamfer option? Okay. Just click the two edges using your left mouse button. You can click one vertical and that horizontal line. And just drag little bit. You'll be able to see the chamfer there actually. Okay. So let's see, we'll give some 8 mm to that chamfer. Okay. So it will basically create like a groove kind of thing. Okay. So you're able to create that. 8 mm. Now I think after you have created that, you can come out of the sketcher using the button. Okay. So now can we extrude this to let's say 200 mm?
The push pull.
Push pull, yeah. You can use the push pull button. So the green, the third one, and then say push pull. I'll extrude this. Push pull to 200. So you'll be able to get this geometry.
How much, sir?
200 mm in the X direction. Okay. So you will get a 3D model with one edge actually.
After that, we can
Chamfered. Yeah, after this you exit. Okay. Okay. Now here comes yeah, 200, 10.
after that, push pull, and after this, 200.
After the and enter the second gate. Now we now we distribution of projects. If you rotate it, So maybe just rotate yours. Take them back to. So that's no benefit. That's a pretty thing. That's a chapter. You extrude 200 you extrude. Yes. So, it just, so this is what it is. In fact, yeah. So, it started.
Progress.
So now what we will do? Let's say we'll create a partition. We'll create a partition. So I want like finer mesh near my weld region for the analysis, and coarser mesh after this region. So for reducing the time as well as the number of elements. So how to do that? For that we can try doing a partition. Okay. Partition means it is called in this it is called a split tool. If you open the third green icon, there will be something called split tool. Okay. So you open the split tool. So in the split tool, you can try using, you can click on your geometry. Okay. So click on this particular plane. There will be a one plane will come here like this. If you highlight, if you click on it, just once again I'll repeat it. It's a little this thing. So you click on this geometry, highlight this geometry, just click on that geometry. It will be in golden color. Okay. Then on your screen, you click your middle mouse button, just give a click after highlighting. Just give a middle mouse button click. It should become this pink color. Just check, highlight it, click it. Yeah, like that. Once it becomes pink color, you just, move your mouse towards any edge actually, any edge or any face you can say, not edge, face. Yeah, that is created on a particular, but we want in this plane, actually. On that vertical face, yeah, there. So here, I'll just select this. Okay. Now I'll just say, I want that split to be made somewhere in the location here. So I'll just put a value there. Let's say minus 10. I'll show you. Yeah. Yeah, I'll repeat it. So once you get the pink color, no, I'll just create a plane here. Okay. So now I want a plane. I want this plane is right now on this face. Okay. I want to move this plane to inner side actually. Okay. So for that, if you want to move it to the inner side, you have to press on the red arrow. Okay. Press on the red arrow. You put a value of minus, let's say minus 20. So you will see the point moving inside. Okay. And if you click your middle mouse button once again, just click it once again, you can find a partition. Okay. So now we have that white dotted line will on the component. So should I repeat this again? Let me. Everybody is able to. Left more but positive. Then even we see it going to see it. There's image 20. Plain vision. So already you're create the order. Yeah, you need to fix this plane. There will be plane here. And you need to move the plane inside. You move the arrow. Here, right? Minus 20. It's a minus 0. We can get up. Then what we do once more in table. So, yes, just middle mouse button is middle mouse button. You click outside the form. Yeah, now it is pink color. No? So pink color, you can just go to that face, that vertical face. Yeah, there you go. Face is not. That click. Now it will be, you give that value. Give minus 20. It goes. So you have to after that, center click. Yes. 20, center. Yes, minus 20. Enter. Again, one more middle mouse button. Now it created that way. Now it will apply that. It will make a split at that particular location. So one more middle mouse button, if you click, it will execute that. Yeah, and right. Multiple clicks are there. It might be some slightly confusing, but if you practice 20 times, you will. So why we are creating this split is basically we are creating some partitions in the geometry so that we can define different mesh densities at different locations. Okay. So now I'll go to meshing. Let's say we will try meshing this. Can you go to this meshing solid mesh? Go to mesh, solid mesh. Okay. Use the 2.5D, the hex mesh. Okay. Just you can see if you try to select this, the whole body is selected, right? Okay, the whole body, the entire body is selected. But I don't want the entire body to select. I want only a particular region which I made a split to select. So for that, there will be an icon here below the solid, that cube. There will be something called cells actually. Just below that cube, actually, there will be one more partitioned cube will be. That cube icon is there, no? So below that one, actually. Cells. Click on that cells. The element type is this one, sir. That 2.5 hexa. Element type linear only. Default.
So do you want to go for both circles?
Yeah. You can give a try mesh by default mesh. You can try selecting the cell. Okay. Give let's say after this entire thing don't select, sir. You select this one, use the cell option, okay, and give a, you can say there is a mesh size, right? It is default 10 mm. Cells. You need to change the size. Now try selecting. Different machines. First you enter the value, then you right. Then check. Keep on. Next keep on. You can make 2 rows on this. How can you center ball? Yeah. Select the plane. There on the screen, on the geometry, you can select the plane. Particular place. Now you give the experience really. But one thing, if it looks like long, okay. Okay. You will see what you're gonna it's a now mesh with the measures. Here you can give maybe 5 2. This will select the entire border. Select the cell. Click on the cell icon. Okay. So we can we'll just live into 5,000 computer. For building, imagine now taking 5M. Everyone you put 5M. என்ன பண்ணிருக்காங்க 8 you put 5M. Small one you put 2M. 2M. Yeah. Right. So I'll also mesh that with 5mm. 2M. Okay. Now I want once I create this, I want a mirror of this one to the other side. Okay. So how do we do that? That we will see. So here for mirroring, you can exit this particular meshing. It is open. You can exit this. So you will get the mesh edge. Okay. So now we have to mirror this to the opposite side. So what we will do is there will be one transform option actually. So here you can see below the meshing, there is one you can say a coordinate kind of thing. Coordinate sign is there. No, that coordinate sign you can click on that. It will open a transform option. Okay. So in the transform option, there is a transform methods. Okay. And there is a transform options coming below that actually. So transform methods and transform options. Okay. So can you click on the second icon in the transform methods? That is a mirror method. Mirror. You can use a mirror method here. I can check. Yeah. Yeah, the second icon here. Okay. Then you can select the second icon in the next one also. Mirror method. Okay. So there are two methods. What it does is, if you select the first one, it will just move. Okay, it will not make a replica of the earlier one. If you select this one, it will move as well as you will be able to retain the original. So it will make a copy of it. Okay. Now how to copy this? So you have selected this option. Next step is click on the geometry. Okay. And you will get a plane kind of thing on the in the screen actually, right? You select the plane here, where this plane, this face, you can see it getting mirrored. If you select the correct plane, no, you will get it will get mirrored in the right location. That vertical plane. Yeah. Little bit you zoom and execute that. Yeah. Then click on the middle mouse button. Click on the middle mouse button. Middle mouse button you click. Yeah. So you'll get a copy of the earlier. Yeah. Because your part turns. Click on this. After that, you can exit the face. Yes. You need more button. One more thing. Ah. These kind of things can be easy. Actually, this is just that part. Then the top box, we have. And the next time, anyway.
Just a minute. Ah, yes.
Yeah.
Advantage.
So now what we'll do is we'll create a bead in between. Okay, weld bead. So weld bead, you already have some points here. Using these points, we'll try to create a triangle like this. Okay. So what we will do is we'll go. I come to this geometry edit tools. Geometry edit tools. Edit tool. This one, third option, third icon. Okay. There you will get something called filler. Filler, yeah, the second line. So can are you able to find the filler option?
Yes, sir.
So there, in the filler option, you click on the filler option, and you can just zoom to this triangular location actually, where we have created the groove. Okay. There you click on, you use your shift button actually. Click on the shift button, press the shift button, then click the 3 points there. Okay. And once you have done that, just release your shift mouse button. It will create a surface. Okay. Yeah. Now what we do is, maybe you can push, do one more thing. You can push this, put this, what do you call this triangle in a different part here. Let's say add part on the, the browser. You can say add part, drag and drop that surface to the part 2. So it will come in a different color, some red color. Now create one more part. You can put it and one part. And from this part. Okay, part is already set up. Yes, take this part. This is this. Spend any move. Drag and drop this out. Yeah. After the line actually it is good. Line going on. Yes. Okay. It will be placed. I said they are one. Surface to part 2. So now you can use the push pull option or to create a 3D of this triangle actually. Okay, so that it will extend towards the entire pillar region. So what we'll do is we'll use the same push pull option. Okay. After click on the push pull, click on this what do you call that triangular surface, and put the value. Like you can say you use the length. You can measure 200, right? So you can give a minus 200 or plus 200, whatever value you give. Yeah. So you can see in which direction it is moving. According to that, you can give the fill. So you can see a red, I can say middle geometry has been created. Okay. Now we can mesh that geometry, no? So go to the solid mesh and you can give a 2 mm mesh, same mesh density, or you can give less also, depends. You can give the same mesh size, whatever you use the center region, so that you will get the bead geometry generated. Okay.
You can do. Oh, right. And find it. Find it. They're going to answer on that. So this one is nice. Maybe what we say is very happy. So it's nice, it's fine. And I was. And then allow them for meeting 9 minutes again. After 8 then also. Can you take up your legs? Right. We go 30 right shortly.
Okay.
It's on the time.
Okay. Shall we go now?
Break 1 minute, sir.
Okay.
So we'll do break, sir.
Okay, sir.
Then we'll continue.
Okay.
We'll try to close this module by today. So I downloaded 3-4 research articles. Let me share it from my system so that they can understand how this simulation is going to help them for publishing papers.
Sure.
And also 2-3 papers I made it. So I will tell what are things I consider for the building, how I made it. So it will be helpful for that option. Dear online participants, and we'll go for tea break and we'll come back after 10 minutes. We'll continue this problem and we'll finish it by today itself. Thank you. Hello. Hello. Seri, okay. Seri, okay. Dear participants, now break time is over. We are joining the session. We'll complete this simulation. After that, I will share my experience, how numerical simulation is helping me to publish a paper in good journal, and how to obtain the data or how to correlate data from the literatures for the numerical simulation. That also I will tell it a little bit. You can catch up. Sure, it will be very helpful for you while going for paper publications in good journals. Thank you.
So we'll try to continue from there. Now, hope everybody is able to create the mesh effects. Okay, so now what we do is we'll export this mesh entities to the effect. So this one, I think they have so drawn or something. What is this? I think it is there on the screen also.
It's in screen. Yeah. It's in screen.
It's in the screen. I think somebody might have drawn something. Okay, no problem. So can we export these two meshes, like these three meshes actually, to plates and then one filler element. Okay. So when you expand your browser model browser, you will see the meshes created actually. Yes.
Sir.
Yeah.
It's to part one.
Not required. Not required. You can export just as. So what you do is you select one mesh. Okay, like this. Okay. So you can say right click and say export. At the bottom, you'll find one export option. Okay. Last one. So then it will say, it will ask a file name. You can put it as mesh1 or you can say left plate, right plate, or let's say plate 1, plate 2, like that you can do. So let's say I'm putting it as my, let's say right plate or something, R plate. You can give your own name to that file actually. And click on save. Yeah, mesh right click, last option export. Okay. So now it will ask for, once you export, it will ask for a unit actually. Okay. You there is a drop down menu and select any unit that you see, ton or mmg, something like that. You select any unit actually, and then you export. Okay. Millimeter. Select any millimeter anyone you select.
Export.
Any select any. Right.
The next is
Next, do this. Repeat the same things for all the three. Second one. Yes, repeat export. Plate. Can put it as a left plate. Another plate.
no, sir.
Which one? Export as video. Video.
So no, sir. No, on me.
Good.
Which one? Sir, on me.
That is because it's everything down. There you can capture. You don't click on solid, you click on mesh. Then it will come as a video. Now you try to. Dot video. Similarly, all the three things we'll export, including that bead. Okay. So after the export is done, done. Now let's open the welding GUI. Welding, simplified welding. Let's open the simplified welding.
This is exported the left and right on the same.
Only one minute.
What the
I feel very sometimes is simplified welding. And the next one. Part two. Parts inside that will right. Yes. You can name many people. You can change the thing, control S or the opportunity. So others. Yeah. So now after opening the Simfet, go to file menu. Open Simfet. Go to the file menu. Create a new project. Okay. Create a new project. You can give your name, your folder, everything. Then give OK. Okay. Then you give OK for that window. Give OK. So now we'll import the geometries. That is our all the PDF files. Yeah, okay. Now you can go to your file and then import all your geometries. Now that is a mesh, whatever we created. Yeah, you can I'll tell you. You can import, go to geometry, then import. You'll just browse to my tutorial. Okay, here you can use like you can use all the three. Like you can use your shift mouse button, control mouse button and select. Yeah, mesh 1, mesh 2 and bead also 3. Open. Then give OK. Okay. All files will be imported in a single shot. Okay. So now you can see the 2 plates. Which ones are?
While importing, general import also.
You can import geometries. Right click on them. Right click into other setup. And select your file list. You created the PDF file from there. That file is fine. That's in different folders. Select control button. Select all your file. Open. Do okay. Yes. So we have imported the geometries now. Now we'll create 2 components in the process actually. Okay. So can you right click on the process in the process tree? Then say new components.
Process.
On the process, right click, sir. Right click your mouse button. And new components. Yeah. New components. New components. In that assignment assistant. Click on assignment assistant. Okay. There you tick two of your plates, no? That you tick. 2 plates. Then say create. So the two plate geometry should come in your screen. Okay, after you click create. May take some time sometimes. Okay, so you'll be able to see the two plates in your screen. Okay. Now let's add a material. You can right click on the material. Material right click. So go to the library. Materials right click library. We want to add the material. That's it. Okay. You choose any material of your choice from the database. Okay. Any material you can choose. Any welding material. Okay. After you have selected the material, if you give OK, you can just drag and drop the material to the process. Okay. Drag and drop into the process. So all the properties will go into the process. Now let's create a temperature. Just give right click on temperatures, new. Just give OK. Don't change anything. You can just give OK. Okay. Drag and drop the temperature to the process. Process. Yeah. Put it in the process. Okay. Next, can you double click on that bead geometry that we created? That bead, whatever is there inside the geometries, there will be a bead geometry that we created. That's mesh it. If you double click it, you'll be able to find see that in the screen. You can see that on the screen. Huh? Double click on it. Okay. So now let's create a trajectory on this particular bead actually. Okay. So I will just take this bead. I will take the trajectory option, right click, create a new weld line. Okay. So like yesterday we selected that cylinder, right? Similarly, yeah. So what you do is you double click on the bead, you'll get the bead geometry, right, on the screen. Now come to the trajectory actually. Okay, right click on the trajectory. Right click on the trajectory, then you will get new weld line. Yeah, the first option. Okay. So try to select a node from the beginning of this. I'll just show you on this thing. You can take the trajectory settings here. So you should try to select the trajectory in such a way that you will get a straight trajectory line along this bead actually. Okay. So I'll just try to show you that. So in the trajectory settings on the side, you can see that select node option, right? Okay. Click on that. Select one point here at almost at the center actually here. Okay, on the center of the trajectory, select one point on the top.
Center means
You can say on the top.
face.
Yeah, on the top face at the center. Okay. So you may not be able to use the path option. If you're not able to use the path option, you can also select the normal way actually, like this, two points. Okay.
2 points enough.
2 points enough. If it is a straight line, it will identify the straight line. Yesterday we selected because it was a curved structure, like a cylinder.
So, at the end.
Yeah, at the end, same like a cylinder. Yeah, at the end, the center you can select.
Yeah.
Okay. Then now you give OK. Okay. Again, you give OK. No problem. Okay. It's able to do, right?
2 points.
2 points enough. Since it is a linear, it will identify the paths.
Okay.
Oh,
Okay.
that's it. Yeah. Select your center. Your piece. No one can use value. You maybe. Here you same opposite side. So we create a project from where to. Now we create a trajectory, now we create the other. Like you can add materials, temperature, or distribution parts. Right, keep materials, you can take a material from the line, any material. Right or this is a plain material. You can use another material for your pillar part. That's it. Geometry, very next. You can export the mesh. Save. Now what you do? Default. You save all in place in a single. Yeah. Yeah. So what to think? Yeah. Yeah. Okay. Yes, sir. Sir, is the color put up? Healing some. It's in the video. Right, so you have yes, sir. So suppose you are taking now. Suppose sorry, okay. Yes. Yes. Session teacher central. Only
Data integrity. Stack is software. Yeah.
So now we have created the trajectory. So after this, what we do, we should create a like robot object actually. Robot. Okay. Okay. Yeah. After trajectory, we should create a let's create a robot. Okay. Let's put all our weld everything into that robot actually. So can you right click on the process? New robots. New robots. Inside the new robot, one more new robot. Click on that new robot. Okay. So you give a material to that robot. It can be same material or you can give a different material according to your choice. You drag and drop the material inside the robot. Just drag and drop the material inside the robot. Okay. Drag and drop the temperature also inside the robot. Okay. And drag and drop the trajectory also inside the. Okay. Done, right? Trajectory. Yeah, trajectory. Right. Then what you do is after you have drag and drop trajectory, drag and drop that bead geometry is there, na? That also you drag and drop inside the row. So it will ask all well lines, just say all well lines. So now you will be able to keep the trajectory. You can take the other way. This is the bead. So that will be the add. Okay. Now let's add some welding parameters. So can you right click on welding parameters? Welding parameters. Yeah, welding parameter. Just below the trajectory, there is welding parameters. So click on the first one. That is the new heat source welding parameter. Okay. So here you just feed in your values like velocity. You can just say, let's say 5 mm per second. Okay. Give a current value according to your requirement. You can give any value. Yeah. Voltage, current. And then efficiency, you can give some 0.9, 0.8. Yeah. Any value you can give. Okay. After that, go to the next heat source. So in the heat source, you can give your Goldak heat source parameters. So you can enter like front length, let's say 2 mm, to rear, let's say some 4. Okay. Depth you can give some, let's say 4. Width you can give some, let's say 4. Depth you can give some, let's say 6. 6. Yeah. So your plate thickness is 10 mm, right? So you can give less than 10 mm. Your depth. Some 6 or 5 you can. If you can use a 2, something like a 2, 4. Like based on your judgment, you can give it. Okay. After that, you can just say okay or apply or okay. Anything you can give. So it will create a heat source. Okay. You can drag and drop that heat source to the trajectory or inside the robot, anywhere. Okay. Now double click on the robot. You can double click on the robot. Okay, there inside you can see the weld sequence. Okay, so let it be default. You can go to the trajectories. Okay. Can you go to the project? So click on projection on surface, the first option. And then the orientation actually. Okay. So the orientation might be not be on like you can say vertical direction. It might be in some inclined or something like that. Okay. So what you can do is if your torch is vertical like this, you can change your orientation like this. Inside the component center, you will get something called global X, Y, Z like that actually. Okay. Three options. So in this case, in which direction it's oriented? In my case, my Z is the vertical axis actually. Okay. In most of the cases, it might be like that. Okay. Just say change your global axis to global that Z actually orientation. Put it to global bracket Z axis. Orientation. No, this one, this one is but the torch is now like this. You want like this, when you do this. You build it. Exact 90 degree will be building. So after doing that, you can give okay. Okay. You just give yes, sir. Okay. So you can see the welding, the robot, angle that is vertical. And also you can see the trajectory as well after doing this. Okay. So now these things are set. Our geometries and robot parameters are set. Now we should give some boundary conditions. Like yesterday, let's create a support in the below of the plate. And then some clamps we will give to hold these plates actually. Okay. Those two we will try. So let's go to the right click on the process. New boundary conditions. Okay. Let's say the first one, the new bearing. Okay. Give OK for the new bearing. Now let's create a generate geometry for the bearing. Okay, generate geometry. You can right click on the bearing, say generate geometry. And in the type, by default, it will be a cylinder. A cylinder will come. You can change that to a cuboid actually. Cuboid. Okay. Then there will be a option. One button will be the select location just below that. This thing. Select location. You click on any location on the bottom side of your plate. Just below that. Just yeah, there. Select bottom side. Bottom side. So that bearing will be created in the bottom. And these geometries you can create in Apex also and you can import. Okay. You don't have to create here. Details. You can come to details. You can increase the dimensions of that cube actually. Let's say width, I'll say 500. Depth also 500. Okay.
The width, what is the width?
Which one? Width you can excuse sir. 500 or 200. It should cover the entire plate. That's it. Yeah. Any value you can give. It should cover the entire plate. And yeah, depth you can give same 500. Then give some height. Does not matter height. You can give some 10 or 20, whatever it is. Okay.
Just okay with this.
Just give okay. Yeah, after that. Okay. So you'll be getting a bearing under the plate geometry actually. That is like a support. Okay. Now let's create two clamps. So clamp at two ends of the plate. You can create two clamps, or if you want, you can create 4 clamps at the corners. Okay. We can try different things. So let's say we'll go to the process, new boundary conditions, new clamping. Okay. So give a force to the clamp. Let's say 0.1 kilonewton or something like that. 0.1 kilonewton force you put it. Okay, you can just say in the force option here, you can just put your force value there. clamping force, right? Yeah. No need to try. Now you will create a clamping geometry. How you created bearing? Like that, you will create a geometry for the clamping edge. So you can right click on the clamping, say generate geometry. Okay. You can create the clamping of your choice. Like you can keep it as a cuboid or a cylinder. Let's say in this case, we'll choose it as a cuboid. Select the location. I'll select anywhere on the top portion. Okay. You can give a width and things like that. So let's say I'll give some 50. So you can give your own like dimension. No need. I mean, any particular dimension actually. This is just to impart a boundary condition on the plate so that the plate force. You give force 0.1 kilonewton. Yeah. Yeah, force you give. Below that, yeah, just below that. Yeah, 0.1. It's in kilonewton, so it will be 100 Newton actually. So can we create one more clamp on the other side of the plate for the other plate as well? Okay. So I'll just go to the clamping. Give same force 0.1 kilonewton. Generate geometry. You can select the location there. Let's say I'll select 50. Hello. So you can see the two, you can just create the two clamps as per those things. Whatever dimensions you want, you can create it. Okay. Create it, right? After doing all this, our entire process tree, everything should be in the black color actually. All the letters should be black. Okay. Everything should be black. Okay. Now, if you have done this, you can just try to run this model actually. You can keep your parallelization if you want, like in the process parameters.
After that, what?
Yeah, after clamping is done. It should be all black, sir, like this.
Right.
Okay, everything is black, right? Okay. Now what you can do is you can go to the process parameters. Double click on the process, the last option, process parameters. You click on parallelization, the second one, second option. Okay. There you give a number of cores. You can give, let's say, 6 number of cores. Like most of the machines will be having 6 core, more than 6 core. So you give 6 there actually. Okay. Done. Then try to run this start analysis.
Okay.
Yeah, okay. Yeah, okay. Then try to run this actually. Play, yeah, green button. So it should start the analysis. So let's, once it starts, once the result starts coming up, it will appear here actually on your process tree itself, below the process parameters. You can double click it and you can check the result actually. Okay. Results down, yeah. Just play that, sir. Down one play button will be there. No, just in that result, one play button is there. Yeah, that one. You'll be able to see the run actually. Okay, progress. You can see the heat source moving actually according to the velocity that we have given. Okay. So here you can see the temperature results like what we saw in the additive. Same, almost a similar GUI. I mean, this thing will be there, results options. So can you right click on the result option here on the results? On the results, can you right click in the process tree in the result? Just right click. You will get something called welding monitor. Okay. Just click on the welding monitor. You will find something called robot. You just click on it actually. Okay. If you click on it, you will be able to see your heat source, that is a weld penetration or the heat affected zone in the model. Okay. So that red zone, whatever you get, it is something like a fusion zone. You can just play that little. It'll come. Play that. Yeah. So that will be your, the fusion zone actually. Okay. Heat affected zone.
See, deformation.
Yes, sir.
How to see the deformation?
Deformation. Deformation, you can go to the result here. There will be something called a total displacement. Okay. This will give you a magnitude of the displacement actually. Okay. Yes, sir. Yes, sure. So let it run for some time, sir. We'll see after it runs, we'll see the result. I'll hand it over to sir for further discussion.
ಮಾತಾಡ್ಸಪ್ಪ ರಮೇಶ್ ಮಾತಾಡ್ತಾ participants ಇಲ್ಲ ಒಂದನ ಇರುತ್ತೆ Give us a percent or co-host of it. Right? From our right. அங்க ஸ்டாப் ஸ்கிரீன் கொடுப்பா இப்பெல்லாம் ஓபன் பண்ணி வச்சுட்டாங்க போனேன் போச்சு யார் வந்தாங்களா? Dear participants, side by side, let us check how to use the data for let us open your let us start with this first paper. So in this paper, I have gone for the experimental numerical studies on gas tungsten arc welding of Ti6Al4 vanadium for bank. Taylor welded bank here we made by connecting two sheets of titanium 6Al4 vanadium. But you can see that thickness is joining dissimilar thickness, dissimilar material with different surface preparations, such as like also for mechanical characterization I using Abagus. Okay. So anyway, first we'll getting inside and we'll see what is I did with the softwares welding analysis. So before that, I want to check out what is the optimal parameter for parameters. I figured out the optimal parameter for welding this Taylor weld bank for titanium. Okay, let us go to the resultant discussion straight away. Let me tell. First, you can see the software. You have created one triangle shape, and that's perfectly. As you can see, first one for bead with 9.5 I have given, and the T maximum temperature what I received is 2219 degrees Celsius, and for 442 degrees Celsius. So these much deviations are there. If another side is 1.6 mm. So now slowly we moved out and we found out the heat input by using this simple calculation. And it's nothing but NITTR is nothing but efficient to find the efficiency through numerical simulation. I is nothing but welding current, that also you have given. V is nothing welding. And I have taken this is mm per second. Most probably you have also selected the same sources and you are also feeding the same type of data for your simulation. And the real time I have performed 27 trials and I got bead profile only. I have gone for 1 point plus 2 mm Taylor bank analysis. So first I have kept the bead profile over there and I found that it was melted and it was having some projections. So that and the cross sectional I have taken temperature is rising above 450 degrees Celsius, it will try to catch up the oxygen, nitrogen, and other elements and different color. If colors are appearing that, your welding is not suitable for engineering applications. And titanium is so costly, so I need to cover the entire area to avoid the contamination. Nearby 400 degrees Celsius, I'm making a line. I found out from 0.2 to 16, that in nearly 14 mm is the distance, that much width I supposed to cover. And also I'm changing the beta translucent. That means it's alpha beta titanium material, because this is tight 6Al 4 vanadium. They are beta, the phase temperature predicting how much area will be, well, the phase transformation will occur, how much area below that graph, and finding how much the heat that is heat treatment area was occurred. Slowly these results are correlated with the numerical simulations, and that's I am getting one paper. And the second part of the analysis, I gone for mechanical analysis, tensile test performance for this is not this one. Yeah, this so this paper also I am using commercially pure titanium, and here I can take the gas junction arc welding parameters, and where we are using for most of the arc welding. And here the parameters which I've taken. In this parameter CF and CR we have taken, where else you are taken as a AF and AR. So that values we are taken from the bead profile. Here this is the case. What will happen if you are waste? I conducted the bead ambient trials to extract the AF and AR value from the bead profile. Also, you have given the depth of penetration as well as width. That should be obtained from the cross-sectional view of the bead profile. You cannot simply give it. I clearly mentioned. So accurately, you have to take it once a sample is prepared. And these are all the equations for 3D are available. So overall, if you are combining, you will get the capital Q. That's a major one. Other else, if you have frontal and rear heat source models, you have to take. And this is the formula for FF and FR. And you have to correlate this FF and FR. These are fractional factors and non-dimensional parameter, I think. Our research work. You can take the existing paper for the bead profile. You can run the simulation, you can find out, and you can match the bead profile with that. And one is for 1.6 mm thickness penetration, another for 2 mm full penetration. Small lines, which is 3 mm interval we taken. We found out the heat rate, how much, and the length is how much. So based on that, we are preparing the shielding gas arrangement for commercially pure titanium, and we have made successful that. Slowly we have eliminated the colorization. We received the bright silver color bead, and also this is mesh. The B diagram B will clearly indicating the end crater comparison with simulated as well as experimental work. The cross sectional we'll gone for the line analysis. With that line profile, we have found out what is the maximum temperature occurred within the welding zone and how long it was transferred. Okay, this is the simulated weld profile for the butt weld joint, and center one indicating the bead profile, and remaining things, that is light orange to red, showing the heat of it is zone. That also we have predicted. Ericsson cupping test will give the elongation straight away. Commercially pure titanium is so affinity to the atmospheric elements. So it is necessary to check after the weld whether it's having the same property or contaminated. If it is contaminated, it will have brittleness. So it will not come for elongation straight away. It will broken into number of pieces. So we conducted the test, Ericsson cupping test. We have received success. This way you can correlate your work. Another one more work I have. Let me check with my Google profile. This may be the work. Let me check. Yes. This paper fully we have immersed with welding simulations. Here in this paper, we are using titanium 6Al4 finding what is the percentage, that efficiency, because here you are giving 0.6. If you are putting 1, we have different type of heat input. So for that, we want to find out what is the optimal efficiency for welding titanium material. So we've taken that as a challenge and we can we proceed. And most probably you have used this type of W circle heat source. From that only you are using what is the width as well as depth, CF, CR values. Okay. So this is the setup which we have made. As you can see, the center portion only is the clamping the specimen, whether you want to clamp the entire specimen or in the particular portion. That also possible in this software. And other softwares, I don't think so. We just clamp on the perfect location only. But here, you can exactly create the dimension how it looks like in the fixtures. So 3-dimensional heat conduction and ellipsoidal source, heat source front and rear, overall heat input we have taken. Without efficiency also. Is the Densel as well as Ericsson cupping test specimen test in the Abagus. Now slowly we have taken and found out from the literature efficiencies are varying from 68 to 79%, and we have no idea how to fix it. And some of them is saying that 50-60%. Of the studies from the literature number 30, we are getting 52 also it's going. So we want to find out what is the correct efficiency for our work. Machine, and we'll checking the heat input. If we 100% efficiency, you are getting 161 as a heat input. If it is 60%, it is 96.6. And you can see nearly 40-60% reductions are there. So we cannot omit this dimensional parameter. So I conducted the simulation. I know what is the bead profile. So I straight away I given 100% efficiency. And the figure 4, the first one, NITTR 100%, heat input is 160. Reducing the efficiency 100 to 90, then it is 2700 something it's coming, then 80, then 70 I came. When I coming to 60, the bead profile which I obtained from the experimental as well as simulations are matching with each other. So I am stopping with this particular point, and also the temperature also it's getting closer to their melting point. The titanium melting point is 1660 degrees Celsius, and you see the temperature is around 1857, which is comparable with that is heat input is 96.6 watt and efficiency for welding titanium with this much shielding gas flow rate is 60%. Whereas when we are going for titanium welding, I told you it will having a great affinity with the atmosphere elements, so we have to give much more shielding gas. Post flow mean before welding the nozzle, welding nozzle, that is 27 liter per minute I have maintained. This is made by the trial and error method. Pre-flow means after the welding, how long it's we gone for 15 to 20 liter per minute flow rate. So the for your work, and also we have taken the temperature contour along the welding directions, and we found out the profile matching, bead profile matching, and that's it. So next part of the study is for the tensile test as well as Richen cupping test. By using abacus, we just spotted the crack propagation area, how the profile is matching with each others. That's it. So this is how also you can use your experimental work with numerical simulation. Your publication is repeated channel. I told you 2 journals I have published, and you can also check Arabian Journal for Science and Technology. It's crossing 2.2 impact factor. Previous one is the advanced material, something it will come. AGMT, something it will come. Springer, that also one of the premier journal. So it's possible to publishing the paper by using numerical simulation. Only thing is you have to find profile rather than temperature profile. Previous paper I have shown how I predicting the beta transformation temperature and how much profile will be getting inside getting the heat treatment, grain gouging where is occurred. All those things I predicted. I have given some lightning over there from the literature. So my papers getting. Also softwares, when you are going, you have to go with some assumption. Slowly, if you are here, if the moving heat source has a coordinator, means what are the things I have taken. And also I have made this workpiece is fixed and this heat source is moving. So many assumptions are there. Experimental setup, you find the results. I hope you will get in successful publications. So any doubts on this, offline as well as online participants? You can type it in the chat box also if you want. We'll clarify and close today's session. Tomorrow's session will start by 8:30. Dear participants, tomorrow's session is starting from 8. So tomorrow's session is starting from 8:30. Any doubts from the offline participants as well as on? Any queries from online participants? Any queries from offline participants? Okay, there is no query, means we can wind up the session. We are installed the nearly 20 licensed version in the CAD lab, and we have given the hands-on training to the participants which are came to offline mode.